Hi guys, welcome back. Myself Akshayan. I'm currently pursuing my BE in SVCA Bangalore. My topic is finite automata in automata theory and compilers. Introduction to finite automata. Finite automata are mathematical models used in automata theory and compilers. They are used to represent and analyze the behavior of systems that have finite number of states. They are widely used in various fields including computer science, linguistics, and artificial intelligence. Components of finite automata. Finite automata consist a set of states, input alphabet, transition function, initial state, and set of final states. The states represent different configuration of the system. The input alphabet defines the set of symbols that the automaton can read. Transition function. The transition function maps the current state and input symbol to the next state. It determines the behavior of automaton as it processes the input. The transition function can be represented as a table or a directed graph. Types of finite automata. Deterministic finite automata has a unique transition for each input symbol and current state. Non-deterministic finite automata (NFA) allows multiple transition for an input symbol and current state. NFA with epsilon moves includes epsilon transitions where no input symbol is consumed. DFA example. Consider a DFA that recognizes strings with an even number of A's. The states labeled are Q0 and Q1, where Q0 is the initial state and Q1 is the final state. The transition table defines the transitions for each symbol and state. Q0, A gives to Q1 and Q1, A gives to Q0. NFA example. Consider an NFA that recognizes strings starting with A and ending with B. The states labeled as Q0, Q1, Q2, where Q0 is the initial state and Q2 is the final state. The transition table defines the transitions for each symbol and state. Q0, A gives Q1, Q1, B gives Q2. Equivalence of DFAs and NFAs. DFAs and NFAs are equivalent in terms of languages they recognize. A DFA can be constructed from an NFA using the subset construction algorithm. An NFA can be constructed from a DFA using power set construction algorithm. Regular languages. Regular languages can be recognized by finite automata. They are a subset of formal languages defined by Chomsky hierarchy. Regular expressions can also represent regular languages. Applications in compilers. Finite automata are used in lexical analysis phase of compilers. They recognize and tokenize the input source code into meaningful units. The regular expressions are often used to define the patterns recognized by the automata. Lexical analysis. Lexical analysis is the process of converting a sequence of characters into a sequence of tokens. The tokens are the smallest meaningful units of a programming language. The finite automaton in lexical analysis is responsible for recognizing and classifying the tokens. Lexical analyzer generator. Lexical analyzer generators such as lex and flex automate the process of constructing lexical analyzers. They take regular expressions as input and generate the corresponding finite automaton. The generated automaton can be used in compiler to perform lexical analysis. Error handling. Finite automata can be extended to handle errors in lexical analysis. Error states can be added to automaton to capture invalid input patterns. Error recovery strategies can be implemented based on automaton's behavior. Optimization techniques. Various optimization techniques can be applied to finite automata. Minimization reduces the number of states in automaton while preserving its language. Determinization converts an NFA to equivalent DFA for efficient processing. Performance considerations. The performance of finite automata depends on the size of the input and the complexity of the automaton. Efficient algorithms such as state elimination and lazy evaluation can be used to improve performance. Finite automata can be implemented in hardware or software for faster processing. Limitations of finite automata. Finite automata can only count finite input. There is no finite automata that can find and recognize set of binary string of equal zeros and ones. It can only have string pattern. Head movement is only one direction. Finite automata have limitations in expressing certain language features. They cannot handle nested structures or maintain complex state information. More expressive models such as push-down automata and turning machines are used for more complex languages. Conclusion. Finite automata play a crucial role in automata theory and compilers. Finite automata are foundational models in computer science and theoretical computer science, particularly in the study of formal languages and computation. They provide a foundation for understanding and analyzing the behavior of finite state systems. Their simplicity and mathematical rigor make them invaluable for theoretical analysis and practical application in various areas, including compiler design, natural language processing, pattern matching, and verification of hardware and software systems. Their application in lexical analysis make them essential for building efficient and reliable compilers. This was all about finite automata and automata theory and compilers. Thank you.